Hi, my name is Alon. I'm a faculty member here in the physics department of Tel Aviv University. I came from doing a postdoc in Caltech for about 3 years, and I started here roughly 3 years ago. The main goal of my research is to understand the interaction between light and matter well enough such that we can control material properties by controlling the properties of light rather than only controlling the properties of the material itself. My lab is very unique to Israel and also worldwide. There are people who are experts in optics who are pursuing similar goals to mine, and there are people who are experts in materials who are pursuing material synthesis on its own. I think I'm the only researcher that I know of, at least, who combines the two, so I can really tailor the material synthesis to my needs for the optical experiments in-house. I don't need to collaborate with external people for that, and therefore I can close those cycles of material growth and optical experiments very fast and in-house. Synthesis of materials is a slow process, which takes a week, 2 weeks. What we're trying to do here is, instead of growing a new material every time, we're dealing with a creature which is basically the material plus light. Its physical properties are changed due to this interaction with light. Light could be changed very fast. You push a button, the intensity of light changes. You push a different button, the wavelength changes or the polarization changes. You're basically creating a very short cycle of changing material properties using some external knob. In particular, I'm interested, for pure scientific reasons, in interesting magnets, interesting materials where magnetism interplays with electronic properties, because those are very interesting physical systems. On the technological front, I'm currently pursuing two things: efficient solar cells and efficient sources for entangled photons. The process I'm trying to use to create them is called spontaneous parametric down conversion. It's indeed a spontaneous process where one photon is dissociated into two photons of lower energy, but we're trying to make it efficient by finding the right materials. My calculations basically say that these materials could be used in very small volumes, let's say on a chip or on the tip of an optical fiber, to create these entangled photons efficiently. I'm working with the same colleagues who were my mentors, people I collaborated with during my PhD, so it really feels like home. I like the research atmosphere here, and I can build everything that I need to do my research here. I am collaborating with people from my field who are growing materials, and they're asking similar questions to mine. The most concrete one is a collaboration with archaeologists. They found interesting shards that have decorations on them from the Middle Bronze Age, and we used our powerful spectroscopic techniques to identify what these pigments are made of. They are pottery ware that were coined red, white and blue. We were focusing on the blue because it's a very rare pigment, and we were saying, hey, this doesn't match any type of blue that we know. And then we realized it's not really blue, it's some sort of a gray, and this led us to a lot of conclusions. They thought that in the Middle Bronze Age, blue pigments were coming from Egypt, or at least inspired by Egyptians who invented the Egyptian blue pigment. It's a collaboration that couldn't have been formed elsewhere, I think. I was super thankful for the Zuckerman Institute for the help in building my lab and filling it up with all the wonderful equipment that helps me do my research. All of those wonderful researchers that the Zuckerman Institute supports, and we're talking and we're chatting and we're brainstorming and we're just having fun, and this is how science happens, from talking to ideas to experiments.